So we have this carbocation. This is 1 degree carbocation. And this carbocation can rearrange to produce a more stable carbocation. So you have to write a structure of more stable carbocation. So in this case, we can do hydride shift, that is hydrogen migrates with bond pair of electron. So in this case, hydrogen migrates with bond pair of electron. This shift is sometimes also called 1,2 hydride shift. So this is an example of 1,2 hydride shift. Now if this happens, we will have a 3 degree carbocation. So we are generating a more stable carbocation. Initially we are having 1 degree carbocation and it rearranges to give a 3 degree carbocation. Now let us try this problem. This time again we have a 1 degree carbocation. So this carbocation is a 1 degree carbocation. It can rearrange to give a more stable carbocation. You have to write a structure of more stable carbocation. So in this case, we can shift methyl group with bond pair of electron, and this shift is called 1,2 methyl shift. You can have any alkyl group here at this position, then we will call 1,2 alkyl shift. So methyl is a special case. So in this case, alkyl group is methyl. So in general we will call this 1,2 alkyl shift. So product after 1,2 methyl shift we will have so this is a 3 degree carbocation and more stable carbocation. Now let us try this problem. So we have two benzene ring attached to this carbon, and one benzene ring contains OMe group attached, and we have 1 degree carbocation. it can rearrange to generate more stable carbocation. So you have to write a structure of more stable carbocation. Now in this case we have two possibilities. Either we can shift phenyl group or we can shift phenyl group that contains OMe group attached. Now OMe group is electron donating group. So this ring has more electron density. So we have two possibilities. Either we can migrate this phenyl group or we can migrate this phenyl group that contains OMe group. This ring has more electron cloud because of OMe group is electron donating group, and this happens through resonance. So in this case, mainly this group will migrate. Migration happens through a transition state. So we can show the transition state. Now this is the transition state of migration. Now this transition state will be stabilized if I have a group that can donate electron to the benzene ring. So transition state is stabilized by a electron donating group. And this is the reason phenyl does not migrates, but phenyl that contains OMe group migrates, because this makes transition state more stable. So this groups makes transition state more stable. Compared to phenyl group. So in this case, final carbocation we will have. So we have phenyl group. We will have two phenyl group attached. And on this carbon we will have two hydrogen and phenyl group with OMe group. So this is again a 3-degree carbocation. More stable carbocation. Now let us try this problem. So we have CH2 double bond C pH CH2 CH2, and then we have carbocation. Now this carbocation rearrange to give a cyclic carbocation. So you have to write the structure of cyclic carbocation. Now what will happen in this case? This double bond will attack on this carbocation. So if this happens, we will have 1, 2, 3, 4, and this carbon is connected to this carbon. So this is carbon number 5. So we will have a 5-membered ring. Carbon number 1, 2, 3, 4, 5. Carbon number 1 contains phenyl group. Carbon number 4 contains 2-methyl group. And carbon number 1 will also have a positive charge because there is a loss of one bond. Carbon number 4 and 5 are connected. So we have shown 4 and 5 are connected. So finally we are generating a 3-degree carbocation. And this carbocation is also resonance stabilized by the benzene ring. So this is a very stable carbocation. Now let us try this problem. Now this carbocation rearranges to give a more stable carbocation, and that carbocation contains 2 rings. So carbocation has 2 rings. So you have to write a structure of this carbocation. And this time again we can attack this double bond to this carbon that contains positive charge. So if I do that, we will have 1, 2, 3, 4, 5, 6 member ring. That is carbon number 6 and carbon number 1 is connected. So we will have 2 6-membered rings. Let us name. So this is carbon number 6 and this is 5, 4, 3, 2, this is 1. Carbon number 1 contains a methyl group. Carbon number 5 will have a positive charge because there is a loss of one bond. So finally we will have this carbocation, and this is a 3-degree carbocation, more stable carbocation. So initially we are having a 2-degree carbocation, and finally we have a 3-degree carbocation. So this is about rearrangement of carbocation. In case of rearrangement of carbocation, it can be done by hydride shift, it can be done by alkyl shift, or it can also be done by attack of a double bond to generate ring. Attack of double bond on carbocation to generate ring. So in some other video we will also explain ring expansion and ring contraction. That can also leads to rearrangement of carbocation.